Hey everyone. So in this video I'd like to talk about the foci of a hyperbola. Just like with ellipses, there are two foci in a hyperbola, and these foci are located along the transverse axis. So this is just the line that goes through the vertices of our hyperbola. So here in our two hyperbola, the horizontal and the vertical hyperbola, here is the transverse axis in our horizontally oriented hyperbola. And here is the transverse axis in our vertical hyperbola. And so the foci, they're located along this transverse axis, and here they're located sort of inside the bowl-shaped part of our hyperbola. And so maybe let me just sketch them here just to show a rough idea of where you can find the foci in a hyperbola. And so what's so special about these foci, these 2 points? Well, the idea is that no matter what point we take on our hyperbola, if we compute the distance between these foci and the point, and take the absolute value of their difference, we get the same value every time. So here if I have d1 and d2 are the distances from the foci to this point, if I take the absolute value of d1 minus d2, I'm going to get the same thing as if I were to take a different point, find their differences, and compute the absolute value of that difference. So here's this different point. Here's the distances. I'll call them d3 and d4. We're going to get the same value here if we take the absolute value of d3 minus d4. Right, this is the case for any point we pick on our hyperbola. So that's what's special about these foci. And so how do we find the location of these foci? Well, here, let me just write it out. So the foci are located c units away from the center along the transverse axis. And so here c you can find by computing, c squared you can find by computing the sum of a squared plus b squared, where a squared and b squared, these are the denominators in our standard form equation of our hyperbola. And so here if we go back up to our picture and our equations above, maybe I'll erase these distances. And so here are the foci that I've kind of plotted out. C is this distance here, from the center to our foci. And so let's say we had foci in this vertically oriented hyperbola as well. C would be this distance. And then how do we find C? Well, we know that C squared is the sum of A squared and B squared. So we can use that to find C. And so similarly in this horizontal hyperbola, if we take A squared plus B squared, these denominators, and add them up, we get C squared. And so taking the square root will give us this distance C that we want to find if we're looking for our foci. And so, this idea that C squared is equal to A squared plus B squared for hyperbolas, this is not something we're going to prove. It's kind of a messy algebraic proof, and I don't think we're going to get so much out of it. So I'm going to leave it out for now and just kind of accept it as fact as we go through some different problems where we try and find the foci. And so the first example I like to look at is here I'd like to find the foci of a hyperbola given by this equation. And so here, we have the equation that c squared is equal to a squared plus b squared. It sounds very familiar, like the Pythagorean theorem. But here, right, a squared is the denominator of this x term in our standard form equation of a hyperbola. So this is a squared. And then here's b squared, right? B squared is 16. And so this tells us that c squared is equal to, what is this? This is 36 plus 16, making c squared equal to, this comes out to 52. And so what's the value of c? Well, I would take plus or minus the square root of 52. And the square root of 52, this can be rewritten as, well, the square root of 4 times the square root of 13. And so c is equal to plus or minus 2, right? The square root of 4 is 2, times the square root of 13. We can't really simplify that anymore. And so what is this telling us? Well, this is, maybe let's sketch out the hyperbola and see where the foci are located in the picture. So here we've got the center in this hyperbola of, this comes out to be -2, +3, right? So here's our x value is going to be -2, right? The opposite of that sign in that x term. And then here we have +3. This is -2, -3 is our center. And what we do is we sort of draw this box, right? A units out to the right and to the left tell us the right and left sides of our box. And so A is equal to 6. So here I go 6 units out to the right, 6 units out to the left. Then I'm going to go 4 units up and down. Right? B in this case is 4 because B squared is 16. Right? So here's our box. And this gives us the diagonals of these lines here, which are the asymptotes of our hyperbola. And so this is a vertically oriented hyperbola because our y term is a positive term, and so we end up with this hyperbola here. So here's the vertex at the top of this box, the bottom of this box, and it sort of opens out towards our asymptotes away from this vertex. Okay, so where are the foci located? Well, here they're along our transverse axis, so along this line here is our transverse axis, this many units away from the center. So adding on 2 square root 13 to the y value of this point is going to give us the new y value of our foci, and subtracting off 2 square root 13 from the y value of the center is going to give us the y value of our other foci. So here, that ends up being, so 2 square root 13. If we add that onto a y value of 3, and we get a point roughly here at -2, 3 plus 2 square root 13. Right, so we're taking our center point and we're adding on 2 square root 13 to the y value, and we're taking our center point and subtracting off 2 square root 13 from the y value. So this is -2, 3, 3, not plus, 3 minus 2 square root 13. Okay, so that's all we did here is we just added and subtracted on the distance c, this distance here, to the y value of the center along the transverse axis. So now let's work through a problem where we do the reverse and we start with some information about the hyperbola and then we build an equation for the hyperbola. So here we want to find an equation for the hyperbola with some vertices that are given at 8, 0 and -8, 0. And then we want to also make sure that the foci in this hyperbola, well, they're going to be 20 units apart. And so here, if we kind of draw out some quick sketch. So here's one point, and here's another. These are the vertices of my hyperbola. And so if the vertices are sort of horizontal to one another, that's telling us we have a horizontally oriented hyperbola. So I can kind of imagine just a rough sketch just to have an idea of what we're dealing with. A hyperbola that looks like so. So here this is the point 8, 0, and this is the point -8, 0. Okay, next thing we know is that we've got 2 foci, and they're going to be located along the transverse axis, so somewhere out here. And we're saying that this distance between the 2 foci, that's 20 units apart. And so these foci, well, they're going to be symmetric about the center. And so here I know that the distance away from the center, from one foci to the center, is 10 units. And so this distance that we've been calling c is equal to 10. And then similarly, we know that this distance from the vertex to the center is going to be, well, because this is a horizontal hyperbola, it's going to be a. Maybe I'll draw it out here on this side. So I'll draw it on the right. This distance, that's a. So we've actually got a lot of the hyperbola already. We know that we've got x minus, actually no, the center is 0, 0. So here we've just got x squared over a squared, and in this case a squared is, a is 8, and so a squared is 64. And we have minus y squared over, we don't know b squared yet. Right, that's something we still have to figure out, is equal to 1. And then we need to incorporate this idea of the foci. Right? We know that there's a relationship between these denominators in the foci, namely that c squared is equal to a squared plus b squared. Well, c is 10, right? So we've got 10 squared is equal to 8 squared, so 64 plus b squared. And so this comes out to be 100 is equal to 64 plus b squared. And this, when we subtract away 64 from both sides, we get 36 is equal to b squared. And this makes b equal to plus or minus 6. And so here, if we square b, that's going to give us the denominator in our hyperbola equation. And so squaring 6 or squaring negative 6 is going to give us 36. So this is the equation of our hyperbola. So the last example I'd like to go over is where we start with this equation here. That's not a very familiar equation of a hyperbola, but we want to show that this equation does correspond to a hyperbola. So if we can put this equation in a very familiar form, what we usually call standard form, then we'll have convinced ourselves that this equation really does correspond to a hyperbola. So if we can put it in the form either x minus h squared over a squared minus y minus k squared over b squared is equal to 1, if we can put the equation in this form, or in the form where we've got the y term as positive, so y minus k squared over b squared minus x minus h squared over a squared is equal to 1. If we could put our equation in either of these two forms, we'll have convinced ourselves that we're really dealing with a hyperbola. And so here, in each of these two equations that we're hoping to put this original equation into the form of, we're dealing with all of the x terms are squared in this underneath the square, and all of the y terms are underneath this square. Right? That's the case in both of these different equations. And so if we want to put our original equation in this form, what we really need to do is try and fit all of the x's under one square and all of the y's under another square. In other words, we need to complete the square. And so here, let's start with our equation. We've got x squared minus y squared is equal to, here I could distribute the 10 to get 10x minus 10y plus 1. And so we want to try and get all the x terms on one side and underneath the square, and all the y terms on one side and underneath the square. So let's move those 10x and 10y over to the left side. Let's subtract away 10x from both sides and add 10y to both sides, giving us x squared minus 10x minus y squared plus 10y is equal to 1. And so let's do this one at a time. I want to try and rewrite this so we've got all the x terms underneath the square. And to do so, we ought to complete the square. And so how do we complete the square with x squared minus 10x? We're asking what expression squares to something that has x squared minus 10x in it. Right? And so here maybe I'll just kind of say it and we can sort of see why. So here x minus 5 squared is the correct thing. Maybe I'll write this off to the left side. So here this is x minus 5 squared. This is an expression which when we write it all out, when we expand it out, that's x minus 5 times x minus 5, And here this comes out to be, well, x times x gives us that x squared we're looking for. We also have the, minus 5x and another minus 5x. This is minus 10x. And then we have minus 5 times minus 5. This is plus 25. So here this is an expression that squares to have an x squared term and a minus 10x term. And so if I were to add 25 to both sides of this equation, we would have an expression that we can rewrite as x minus 5 squared. Right here, if I rewrite this left-hand side, if I add a 25 to the left side, and I can only do that if I add 25 to the right side. Maybe I'll write it in pink. So here, plus 25 y minus y squared plus 10y is equal to 1 plus 25. And I'm just adding 25 to both sides. Well, all of a sudden, this x squared minus 10x plus 25 is exactly equivalent to this x minus 5 squared. And so all this work just to figure out what number we need to add to both sides of the equation so that we end up with this expression that I can rewrite as a square, as x minus 5 squared. And this minus 5 was exactly the right number so that when I squared them out, I got this minus 10x. Okay, so here I'm going to rewrite this part that's underlined in blue. That's equivalent to x minus 5 squared. And I have minus y squared plus 10y is equal to 26. So now we just need to do the same thing to the y terms in this equation. We need to complete the square for the y terms in this equation. And it's really hard to complete the square when we have a leading coefficient for our y squared term that's not 1. So let's factor out that negative sign through the y terms just to make sure we have this easiest situation to work with here. So here, I'm going to rewrite our equation, x minus 5 squared. I'm going to factor out that negative sign. And if I factor out that negative sign, here I'm going to factor out of that 10y as well. So it's going to be minus 10y is equal to 26. And so this is just so that now our y terms, if I kind of think of them together, that leading term is just 1. It has a coefficient of 1. And so now we want to complete the square for this expression, y squared minus 10y. Well, that's no different from what we had for the x terms, except now we're dealing with a y instead of an x, right? Here we had x squared minus 10x. Now we're trying to complete the square for y squared minus 10y. We're going to have the same thing, right? So here, 5y minus 5 squared. Right, this is the same as y minus 5 times y minus 5. In other words, y squared minus 10y plus 25. So if I had a 25, an extra 25 that was added in here, I can rewrite this term, this part of our expression as y minus 5 squared. And so let me do that. Let me add in 25 into the parentheses here. We have x minus 5 squared minus y squared minus 10y. I'm going to add in 25. And so this is equal to, well, we still have that right side of 26. Now I can't just add 25 into the parentheses on this left side of the equation for free, right? We can't change the left side of the equation without changing the right side the same way. And this is a part where it gets a little confusing. So I added 25 here, but really on this left-hand side, if I kind of look at the big picture, you know, this 25 that I've added in here, it really would come out negative, right? There's this negative sign that's outside of the parentheses that would be distributed into this 25, right? So really, although I've written plus 25 here, this is really minus 25 on the left-hand side because there's that negative sign outside the parentheses. And so to do the same thing on the right side of the equation, I need to also subtract away 25. And now we're really in the clear. Here, this expression, this y expression in the parentheses, that's the same one here that we've said is equivalent to y minus 5 squared. So here we have x minus 5 squared minus y minus 5 squared is equal to 26 minus 25 is equal to 1. And so this is a hyperbola. looks a little bit different because we don't have the denominators, but I can imagine this, each of these terms as having a denominator of 1. So now it's telling me that a squared is equal to 1, and here b squared is equal to 1. So this is a hyperbola with the center at the point 5, 5, and a values and b values of 1. And so here we really convinced ourselves, we've answered the first part of this problem that says, show that the equation is a hyperbola. Well, we've shown that the equation is equivalent to one of these standard form equations. We've shown that it really corresponds to a hyperbola. Now the next thing we want to do is find the location of the foci. So let's go back down here. We said that a squared plus b squared is equal to 1, and we know that c squared is equivalent to a squared plus b squared. So c squared is equal to, well, this is 1 plus 1, and so c squared is equal to 2. And so this makes c equal to plus or minus the square root of 2. So if I just draw a quick sketch of the graph, the hyperbola we have here. So we've got center at the point 5, 5, so maybe I'll just plot it here. So that's the point 5, 5. And we know that a and b are 1, so if I go 1 unit to the left, 1 unit to the right, 1 unit up and 1 unit down, I have the box I use to draw the asymptotes. And so these are asymptotes that are nice diagonal lines with a slope of 1 and a slope of -1. And so this is what is this? This is a horizontally oriented hyperbola. So here's the vertex on the right side. And here's the vertex on the left side. So let me redraw that part. So there's our hyperbola. And we're saying that if we add square root of 2 to both sides in the x direction, and if we subtract away the square root of 2 in the x direction from our center, we're going to end up with our foci. And so the square root of 2 is roughly 1.4, so here it's like 0.4 past this vertex point, and here 0.4 past this vertex point. These are the location of our foci. Maybe I'll write them out. So here the center was at 5, 5, so it's going to be 5 plus the square root of 2 in the x-coordinate, because this is a horizontally oriented hyperbola, and the foci are listed c units in the direction that the hyperbola is oriented. So this is 5 plus the square root of 2, 5, and then this is 5 minus the square root of 2, 5.